My name is Matt Morgan. I'm an application engineer at GoEngineer. Welcome to our webinar titled App-Enabled Devices Are Hot, Flow Simulation Can Keep Them Cool. Today what I want to talk about is electronics getting smaller and smaller, getting jammed into tinier places, and the average consumer is wanting more and more out of each of their electronic devices. Just for a quick example of kind of some of what we're going to talk about today, we have this simple mechanical design that served us well for many years, the thermostat in your home. If we take a look at some of the new things that the market has added, the Nest thermostat is a great example. It's what I like to say, if it ain't broke, it doesn't have enough features. And what you can see is they've added an LCD display. It's network operated, so it can connect to your Wi-Fi and you can operate it from your phone. So it's an app enabled. They've added motion sensors so they can tell when there's activity in your home to adjust the temperature based on when people are there. A lot more is being done in a lot smaller spaces, and this adds heat to the scenario when you add more and more electronics. So our flow simulation software is a great tool to help figure out how much cooling we need. Do we have enough cooling? Do we need to add heat sinks, fans? Especially something like this particular device, the Nest. There isn't any fans on it. You don't want any loud noises either, so they need to make sure that there's enough ventilation or airflow through these electronic components. So flow simulation is a powerful tool to help figure that out. Maybe even positioning components, move them around, what gives us the ideal situation. Okay. So what is flow really here to help us with, and what are we going to talk about today? We're going to look at fluid flow with heat transfer, some of the capabilities that you get with the electronics cooling module, which is an additional part of flow simulation. If you work with a lot of electronics, you can add that on to your flow simulation capabilities. We'll talk about some of the things that adds. It helps you understand what flow simulation can do to help with that design process. What can you figure out before you actually make a product and have to build it? And you can share that information and ideas with other people on the team and figure out what's the best solution. All right, so what is SOLIDWORKS Flow Simulation? It's a general purpose fluid flow and heat transfer simulation tool, but there's so much more to it. It's integrated in SOLIDWORKS. You can check the performance of your products, internal, external flows, incompressible and compressible fluids. We can look at non-Newtonian or Newtonian fluids. All sorts of different flow scenarios. So we can cover a lot of different options, a lot of different environments, obviously not just electronics like we're talking about today. There's a lot of potential for uses with our flow simulation product. Okay. Usually in the past, your engineering process or your design kind of goes through concept modeling, detailed design, then your fluid dynamics happens after. When you start analyzing, sometimes you might even have to create a model and do physical testing before you can figure out what's happening with the flow. What SOLIDWORKS Flow Simulation allows you to do is move that into the concept design and your design process to help figure out what is a good design before we make any prototypes or actually do any physical testing. We can figure out what the best design tools are by just trying a few things with the flow simulation tool. Decreasing the time to market so you're not having to build a model, then change it and build a model again and do some physical testing. Lets you figure that stuff out beforehand. So really it allows you to create more innovative designs, try a bunch of different scenarios, think outside the box a little bit and try something maybe that you haven't done before. You know what has been done in the past and what's worked, but what could make things better? How can you improve it? So flow simulation lets you try those different markets, or different options, I should say. Okay, flow simulation is used in a wide variety of industries. It's not just electronics, it's not just aerospace or any of those different things. There's a wide variety of uses for it. You can kind of get an idea of some of the common uses for it here. If we take a look at this screen full of images, it just kind of gives you an idea of all the different potential uses of SOLIDWORKS. We have the medical industry down here with looking at arteries with different devices to help stretch out arteries and how the blood would flow through there, to valves, to airflow or water flow in this case around objects. A wide variety of potential uses for flow simulation. Okay, so what we're going to talk about today is compact design of a CPU enclosure. We're going to look at fans, where to place fans, how many fans are necessary, what's the best configuration for those fans. And so here's an example of the object that we're going to go through. There's some vents on the top. We want to look at the vents being in the model or not, which gives us the best cooling of our electronic components. We have outlet here and the fans are on the other side. We want to try one with the vents, without the vents, one with 1, 2, or 3 fans, and see which one gives us the best properties. Oftentimes you might even be surprised with what gives us the best results. Here's our constraints. We have processor, some IC packages. Those are going to be these transistors on the side, and the RAM chips over here. We want to look at the temperature of those. That's primarily what we're interested in this design. And we want to look at these limits. We don't want it to go over 68 degrees Celsius, 95 for the IC, and 59 for the RAM chips. So we need to look at packaging, fan configuration. We want to minimize the heat buildup and also optimize fan power, the consumption, how much electricity is it using. If we can get away with 1 or 2 fans, it's better. So let's jump into our design and let's take a look at it. So basically, Flow Simulation is an add-in to SOLIDWORKS. So we simply go to our add-in list and turn it on, and it turns on some new toolbar options, and it adds a Flow Simulation category to our feature manager. So we'll add another tab on there as soon as it loads up. So we have our results here. What I want to do is take you through the process of starting a new analysis and show you what it takes to begin a new one. So we have some examples here of ones that are already done, and we'll go through some of those because the flow simulation studies can take anywhere from 5 minutes to 5 days, depending on how much complexity you have in your model and how many fluid cells are in your study. So let's start a new project. The easiest way to do that is with the wizard. The wizard walks you through the requirements to set up. So we'll call this the webinar project. We'll use the current configuration. You can see I can put multiple studies in one configuration, or I can take advantage of multiple configurations. One that has the slots in the top. This one that we're looking at doesn't have the slots in the top, so there's no vents on top. So we're basically specifying the units. We're going to use SI units. We can say, but we want to change a few things. Maybe we want it's a smaller size, so maybe we'll look in millimeters instead of meters for length. Temperature, we'll use Celsius. We can change those. We can also save these as one of our unit systems. If you have one that you already know you use and you like and you always use the same units, you can save a new unit system. That's easy to do. We want to do an internal study. External, you just check this on. We want to include heat conduction in solids. So we're going to turn that on. You can do just heat only without convection into the air, but in this case we're going to be solving there. That's one of the values of using a flow simulation tool, is that we can get true convection instead of in our regular simulation professional that you get when you get into static linear analysis and thermal and frequency. Thermal analysis, you're applying a convection coefficient, so you're kind of making assumptions on what the convection is. In flow, you're actually solving the fluid and you're getting true convection values based on the fluid's temperature, its turbulence, all that kind of stuff. So you're getting a lot more accurate results. You can even include radiation if you have really high amounts of heat, and radiation is a transfer of heat method. You can look at time-dependent gravity if you want to include buoyant effects where air rises when it gets hot. Rotation, if you actually modeled the fans in and wanted to look at how the fans would work, you can create rotating regions around the fans to simulate the fans' movement. Okay. Then we get into defining what materials we're using. In this case, we're just going to use air. So we'll define air as our default fluid. You do have some options as far as, are we going to see high Mach numbers? Do we need to calculate up into the higher Mach numbers and some of the shock waves that creates? Not in this case. We can include humidity as well. At this point, because we're looking at heat conduction in solids, we're going to determine which is the most common material type. And so the most common material is going to be a typical chip array, and that's going to be in, let's see, IC packages, typical chip array. This is one of the things that you get with the electronics cooling module, is a lot more material types in here. When you just have SOLIDWORKS Flow by itself, it's very, I mean, it has a lot of materials, but it's definitely not nearly as populated as when you have electronics module. You get something like 14 or 15 materials, I believe, if I remember right. And when you add the electronics cooling module, you get more in the hundreds range, you know. Of course, you can add your own materials. So if you have the material properties of any fluid, you can add those in either package, whether you have the electronics cooling module or just flow simulation by itself. You can always add your own material properties. But these ones come with it, so it helps save you some time so you don't have to add them yourself. In this particular case, you can use all sorts of different wall conditions. This basically is just determining the outer wall. Since we're doing an internal analysis, we want to also simulate that heat is going to leave the system through the wall of this CPU housing as well. So we're going to use a heat transfer coefficient, and we're going to specify a heat transfer coefficient of 8 watts per meter squared Kelvin. So we'll put 8 in there. We'll keep the temperature at the default room temperature. You can add a surface finish to help kind of simulate a surface finish or texture on your walls. We'll just leave it at 0, like it's perfectly smooth. You can set up your initial boundary conditions. Usually these are going to be set up when you have an external study, so you can say it's you know, if wind or something like that, you can specify the speed of it. But we'll just leave that alone. Now this is where we can specify the mesh size. Basically what flow simulation is doing is going to create a bunch of cubed pipettes, is what they're called. Those are the mesh. It's a finite volume mesh. When we look at flow simulation, it's not a finite element if you're used to simulation analysis. The flow simulation uses the finite volume mesh, so they're basically cubes. This is specifying the size of them. You can basically, each time you drag this a tick mark, it's cutting each cube in X, Y, and Z, so it takes one cube and turns into 8 each tick mark down. When you go to 6 or higher, then it starts doing some mesh refinement while it's calculating the results. So if it sees fast-moving regions, it'll make the mesh finer in that area to make sure it accurately calculates the difference between fast and slow-moving regions. And 6 and higher will automatically refine as it solves. You can also specify minimum gap thicknesses or sizes. So I can say the minimum gap size is you know, based on the size of the model. So if I just zoom in and look at some of these really small components in here, I can measure this and say we're looking at 0.5 millimeters is the minimum wall thickness, and then gap size, maybe in this area is the smallest gap. Let's clear that out and do, zoom in a little. Maybe I'll use the G on the keyboard. Lets me zoom in, pick small objects. So it looks like about 1 millimeter for gap and 0.5 millimeter for wall thickness. So I'll just go back in. I already hit OK, but you can still edit the initial mesh here. So I can say, okay, minimum gap size is going to be 1 millimeter. Minimum wall thickness will be 0.5. That just means that the mesh will make sure that if it finds a wall that's that small, it'll make sure there's enough elements in it to accurately depict it as the flow region flows around it. Without that, you might get areas where flow will go through a thin wall because the mesh isn't fine enough. So we'll specify that smaller number to make sure that it gives us accurate results around those objects. Okay. So now we have the main study set up. You can basically go in and define materials. If we insert materials, we have a list of predefined materials. You can just pick the parts in the graphics area or the tree to define them. When you have the electronics cooling module, there's definitely a lot more materials in here. You can also see that you can define your own. So user defined, if you hit create edit right here in any of these places that defines either fluid or solid materials or fans or any of those kinds of things, you can edit your engineering database right here. So you can see my solids is in here. I could add a new one and specify whatever I want the different materials properties to be. So we have a mineral oil one. I think this is in the default, but I've copied it and made a few changes to it. But you have some different numbers for its values. You can use tables and curves for any of it. So if you're looking at the electronics coolant module, it can include thermal conductivity as well. But you could specify anything based on its table too. So you could specify the density changes based on what its temperature is, so you could use tables or things like that. Okay. If we look, so let's cancel out of that. Don't want to save any changes to that. I'm going to go to one of the studies that's already done and take a look at it. So if we switch to this fans with slot configuration, that'll be our first study. Basically what they did here was created a lid. Basically every opening in here would need a lid. So these components are actually not open. There's just a face that we can specify what the inlet and outlet would be. And so these are going to be the fan inlets, and the outlet will be here. You can basically specify perforated plates. So that's how the outlet is set up. If you remember from the PowerPoint, it showed a bunch of holes in here. So we're just going to simulate that as a circle with a certain amount of area of open space. So in this case, it ends up being about half of the area is open to holes and the other half is closed. So the same with these walls. We basically just specify a ratio of open versus closed space, so you don't have to model in every little hole and you don't have to mesh every little hole. It just restricts the airflow based on what that area of open space would be. So you can see they've already defined some material properties. We have aluminum 6061 on some of the heat sinks. We have ABS on the outer surface. You can see that there's no actual opening in here. With the flow analysis, you can either leave it closed like this or have an opening. If you have an opening, to make it an internal study, you do have to close it off so it's watertight. And Flow Simulation gives you some tools to create lids automatically, or you can just put your own lid shape in. This lid shape works well if it's just a planar surface that has a hole in it, and you can cap it with a lid. You can also make your own lids or whatever you need to make it work. But in this case, they just left it closed and created some geometry inside to simulate the open area in the fan. So there's the center is just basically where the center of the fan would be that doesn't blow any air. So we have the materials defined. We have boundary conditions. So we've added an environment pressure on the outside, just at air pressure at sea level to simulate regular outlet pressure, and an environment pressure at the slot area. Okay. Then at the inlet, there's been fans created. So if I edit the definition of one of these, we'll take a look at what that looks like. We have a big list of fans. In the regular version of simulation, I believe you get these fans. So there's quite a few in here as well. Once we open each of these, there's several different fans in each of these. So these just have the fan curves that are giving you what the airflow would be based on different pressure differentials. So we can look at with the electronics cooling module, we're getting some additional fan types, some additional fans based on different brands and things like that. So those are defined. They are specifying the different turbulence, the inlet, any of that kind of stuff. We're having a external inlet fan. But you can specify, if there's baffles on it, you can specify so the fluid comes in straight, or you can have it come in swirling in. These different fans have different definitions like that. Okay. You can also input inlet. So if I insert a boundary condition, these are the types of boundary conditions. The outlet is going to be here. The inlet is going to be here. You can basically whatever you know. If you know how much volume is coming in, how much mass is coming in, what the pressure differential is, you can specify any of that information for the inlet. We're using a fan in this case. Outlet can be static pressure or total pressure or environment pressure. Environment pressure is great if you have a vortex where air is leaving and coming back in. If it's cycling because of low or high pressure, then environment pressure works better in that case. We can even go into wall situations where our wall can have motion. You know, if you're simulating a truck driving on the road is moving, but the truck is kind of held still based on the way the study is solving it. So it simulates the wall moving to represent the road moving, and then you're just applying a wind speed to the truck. But this can give you more accurate results along the region where the road is. You know, a lot of different situations where you might want to have a moving wall. Okay, so that's pretty much the setup. We have some heat sources defined. These are basically volume heat sources. You can do volume or surface heat sources. So if you know the temperature of a surface, you can just apply that. You can apply the different heat sources. So this we're determining the wattage of each of these different components. So you can see there's quite a few different heat sources defined. Some are just temperature. Some are heat sources. It's just to show a variety of options, really. Okay. Then we get into, those are perforated plates. So these perforated plates, you're basically creating either a predefined perforated plate. So, you know, the slots will be rectangular holes, round holes. You can also define your own. You can see in this case, the circular holes in the electronics box has diameter hole size of this, and the area of open space to holes is that. It's a ratio. Okay. Now, in the next two things that are set up here, these are specific to the electronics cooling module that you can add to Flow Simulation. The two resistor component, this is going to simulate your processor where you have the case and the junction. If I read from the help menu, it says a two resistor model implemented in Flow Simulation can be used for simplified solving of heat transfer problems in an electronic device with small electronic packages, chips, etc. A small package is considered as consisting of two flat solid plates, junction and case, which are mounted on the board. The junction represents a die or chip. The case represents the die's case. The heat conduction through the chip is calculated using specified thermal resistances to heat conduction from junction to case and from junction to board. The junction and case plates are mounted as a high conductivity bodies with heat insulating sidewalls, so the only cases top and junction's bottom transfer heat to the surroundings. So that's something that you get with the electronic cooling module. A couple things that aren't in here is electronic cooling module also includes Joule heating. It can solve heat pipes, and then another one that it adds, obviously materials we've mentioned. It also added printed circuit boards. So if I define printed circuit boards, again, you can get predefined circuit boards, or you can enter your own properties. And if I take a look at one of these, you have different. I'll just let you guys look at this. If you guys do electronics, this is going to make more sense to you. If I look at some of the tables, like the conducting layers table, you can kind of get an idea of how many layers you're putting in and what the percentage of conducting material, in most cases copper, I would assume, is on that layer. So you can kind of get some different heat transfer properties based on how many layers your PCB board has. That's unique to the electronics cooling module, is the properties to be able to simulate the electronics circuit board more realistically. Okay. Another thing that I believe is unique to our Flow Simulation software is the idea of creating goals. A goal is basically telling the software what's important to you. So as it's going through its solution process, it will show you what is important, and it will also stop the calculation when it's achieved accuracy on the things that are important to you. If you're not worried about pressure, then you don't have to solve pressure. If you're just looking at velocity and temperature of components, then you set those as goals. So these goals have been set up where we want to know what the maximum temperature of the fluid is. The main chip temperature is what's critical to us. So basically, to define these goals, you right-click on the goals, you say insert either global goals, which are just like everything. You're looking at all the fluid temperature, anything like that. You can set up goals at specific points. If you wanted to figure out what the temperature is at this corner, you could do a point goal. Surface goal would just be, you know, any face or combination of faces of a part. Volume goals would be the entire part, not just faces of it. Equation goals could do things like calculate the Reynolds number when you're looking at turbulence properties, different things like that. Or I could have a goal that says, I want to know what each of those RAM chips temperature is, but I also want to look at a goal that gives me a temperature of all of them combined. So I could say, I just want to know what the temperature, or like the average temperature, let's say. So you could do an equation that says max temperature of each one divided by the number of them and get the average temperature across all the RAM chips. Okay, equation goals are good for that. So basically, these are volume goals. So to create this, you would insert a volume goal, you'd pick a component, and then you would say, okay, what is it that my goal is? Am I looking at the solid volume? Am I looking at fluid volume? Am I looking at temperature, velocity of fluid around that object, obviously, since it's a volume goal. But I can look at the pressure against it, so I can use that pressure to help do a stress analysis later if I wanted to. The temperature of the fluid, temperature of the solid is in here. There's also, for solid bodies, you can look at the force in X, Y, or Z, all kinds of things to figure out how much drag is on a component, anything like that with the volume or surface goals. So once the study is run, let me take this project. Now let's just take this one and clone it. So I'm going to create another one. Clone is basically just duplicating that study. So I can duplicate a study that I've already spent the time setting up, and then make a few modifications and run a brand new study. Okay. So if I create that study, clone it, it's going to copy all of the setup, everything to it, and then I can run it and kind of show you what the run dialog box looks like. Because while it's running, I can look at information like the goal convergence plot. How close is the goal to solving? So if I say I'm interested in the temperature of the fluid, how close is that goal to achieving accurate results? You can also look at a cross-section while it's running, so I can kind of watch how the flow is developing as it's running through the study, and get an idea of how long the study is going to take to run and so forth. So I just want to show you what the run looks like for a minute. I think these take in the 5 to 10 minute range to run each. I just ran them all at the same time with the batch run, so that is another option too, to run all your studies. I could set up all these studies and then just run them over night or over a weekend or something like that if you wanted to have it run a whole bunch of different studies. Flow does also support network solving, so I could send a study to run on another computer. When I tell it to run, I can tell it to run on another computer. It does only require the license of the computer that is initiating the study. So you could have one flow license and still run the study on another computer to help save processing time or to use more processors. So we don't limit you to processors like some of our competitors will. They'll only allow you to run on certain processors. So that comes in pretty handy. Okay, so let's take a look at running this study and give you an idea of what the run dialog box looks like. So we're going to create a new calculation, solve it, and mesh it. So we'll take a look at the dialog box you get while it's running. The nice thing about the flow simulation too is that you can stop the solution at any time and view the results as far as it has run too. So if you wanted to take a look at it in the first 5 minutes of its run and see if it seems to be flowing the way you expect, at least, you can stop it. You can take a look at the results, and then you can start the calculation. It will continue from where it left off. So when you rerun it again, it just says new calculation or continue from where you left off. And so you can take a look at that anytime and still continue to run the solution after, unlike a stress analysis where you kind of have to wait for the whole thing, unless it's a nonlinear study. So the first step is going to be to capture the mesh and save that to the disk, and then it's going to start the calculation. So looks like I already have it set up to using us to showing some plots. So let's kill those and show you how to create them. So I can say insert a goal plot, and I can pick on which goals I want to look at. I'll just look at all of them. So that gives me a list of all the goals, and then as it goes through each calculation, it's still starting the calculation, so I don't see any results yet, but as it goes through the different iterations, we'll start watching where it's bouncing around to until it starts to level off and start to achieve accuracy. We'll be able to watch those. While that's thinking, I'll come back to it. We can also create a section view, and so I can create a section view, and I think the top plane goes right through the middle. Yeah, so we'll use the top plane, and you can look at, you know, temperature, pressure, all kinds of stuff, whatever you want to visualize. There's a lot of different values you can view during the study. So let's just look at temperature. Oh, and you can specify the size of it too, so you can make the plot bigger or smaller. So as it goes through its iteration right now, it's just showing the temperature. There's really no flow coming out of the fans. It's slowly ramping up the flow, and that flow will eventually develop and exit through the outlets, and we'll be able to see how that calculates. But it looks like, I don't think it took that long really to run. I think part of it is that I have the webinar session open, PowerPoint and stuff. It seems like it took more like 10 or 15 minutes for each study, but maybe I'm wrong. I walked away from my computer, but I don't think it was. I ran like 8 studies, and it seems like it only took 2 hours at the most. So that might change. This is kind of like Windows, where it thinks it'll take this long, but it doesn't quite take so long. But we could watch this, come back to it later, and watch how the flow is developing. Maybe this one was run at a higher resolution, so it is taking longer to solve, but I don't know. I didn't set all this up. But here's the goal plots. You'll start seeing them changing a lot at first until they start to converge on accurate results. Then they'll start leveling off. And you can visualize that and see what percentage of progress. Usually you don't see a lot of progress until it gets close. Then it goes pretty quickly. But you can see as it goes through each of those iterations, what the results are, what it's looking like, and you'll start to see the flow coming out of these fans as it starts moving faster and faster. You can see a little bit of the air heating up around these right now, because we're not really seeing the flow developing yet from the fans. So anyway, you could stop it here and save the results up to this point. Obviously, they're going to be very inaccurate at this point, stopping them so early, but I'm not going to save them because I already have the results. So I'll wait for it to, oh, it is completed now. So let's look at some of the results that are already here. If we show the fan with the slot, let it take a second to switch over to this study, and then I'll load the results and take a look at them. Loading the results is just a load. All the results get saved to the disk, so it's just loading those results off the disk with each study. Okay, so there's a lot of different kinds of plots you can get at it to help visualize the results. You can take a look at section views. This is what the completed section view would look like, similar to the one that we just were looking at. However, this one does include the ISO lines that you're looking at, or the streamlines, I should say. The streamlines are GPU based, so as I zoom in, they get more accurate, and zoom out, they decrease. So it's only showing accuracy when you get really close into it. Save you some time as your zoom pan rotate. It's not calculating too much when you're at a farther away level. But we're basically looking at temperature of fluid here. There's quite a few different plots you can look at if you want. We can also look at surface plots. Surface plots are, showing the results. This is pretty similar in temperature. We can double click and change to just plot maximum and plot minimum to help orient the numbers to match. It looks like most of the temperature is hot down right where it contacts the object, so you can't see it as good. But I believe one of these I have showing a wider variety of materials here. Yeah, this one I think shows more, so let's show this surface plot. I think because it's shown more, it'll take just a little bit longer to generate the plot. Oh, nope. just need to zoom out. So this one is just showing the IC packages, all the transistors, and what their temperatures are. Let's just show a couple of these all at the same time. So with Flow, you can also do section views. You can hide components and still look at the plot results with components hidden, things like that. But like this is just the RAM chips, so we can get an idea of what each of those chip temperatures are. One of my favorite ones to look at is going to be the flow trajectories. Before we do that, let's just look at the ISO surfaces. ISO surfaces are basically just showing everywhere that the fluid is a specific temperature. So I turn on ISO surfaces, it kind of gives you just an area of where all the fluid is at that temperature. So, you know, we're looking at something around 26 or so degrees Celsius. So it can kind of give you cloud front temperatures or whatever you want to call it for the surface that represents that temperature in the fluid. Flow trajectories can show us a 3D view of where the fluid is going, how it's flowing. We can show it in velocity or temperature or whatever you want just by clicking on what it's showing here. You can switch it to any other object. So if you want to look at temperature, we could see the temperature's pretty consistent, you know, until you get close to some of these objects that are warm. You start getting a little more heat in here. My favorite is to take a look at the flow in spheres. So this is going to generate the same kind of flow trajectory, but in a bunch of spheres. And if I'm just looking at it static, it's not as good as the tubes or the arrows like we saw before. But this one animates really well. If I just right-click on it, I can play it, and it will show me, based on right now it's set to velocity, so the red is the fastest velocity. But it lets me see where all the air is moving, where it's moving quickly, where I'm seeing swirling, where I'm seeing stagnant spots, where air isn't moving as quickly. I can really take a look at those different options. So a lot of cool things that you can look at in Flow. Let's go ahead and stop that one. Move down the list a little bit. You can do particle studies where you introduce, you know, like sand or dust into the scenario and find out where it would collect or where it would end up. You can look at surface parameters. So these are basically just like a table, an Excel table of what the temperature is or something like that. Goal plots are the easiest, so by specifying your goal, you're also telling it what you want to be able to look at after. So by showing a goal plot, I could say, let's just look at all of them, either show them in Excel or just show them in the box down at the bottom. Every one of those goals tells me what the value of the max temperature of the fluid, or what the temperature of the main chip is, what the RAM chips are, each individual one. And the rest of these numbers are basically during the calculation, but really this number is the one that we want to look at on the far left there. That's telling me what the temperatures are. Okay, so by using those goals and creating multiple studies, we can go through and calculate what options are the best. 3 fans, do we want the slots on the top? Is 1 fan right by the processor going to be enough to keep it cool and minimize how much electricity it uses? If we switch to our PowerPoint, I have some of those already defined here. So we switch through. First of all, do we put the vent on top or not? If we look at the vent versus the no vent, the vents are blue, the no vent is red. We actually see, let's see. So the vents help on the CPU and the IC packages, but it's not as good on the RAM chips. Okay. Sometimes adding a vent just allows the air that's blowing from the fan to just escape out the vents instead of going over the components that we're after. So it helps us visualize and figure that out, which one is better, which gives us a better option. Okay. If we take a look at fan placement, based on the different studies, you can see, sorry, I didn't check to make sure these didn't go over each other, but A, B, and C fan is A is the bottom, B is the middle, and C is the top. So the fans by themselves, you know, we don't really have good scenarios if we just use A or B, but C is not too bad. The temperature of the main processor is lower. If we combine A and B, A and C, or B and C, we get some other results too that are really quite close. If we switch to a chart that shows all of them, you can kind of see where A, B, and C all together is not always the best. Having all three fans, it's actually better for the CPU to just have C by itself, because it's just one fan blowing right on C. But then there's some, vortices around other areas that are making C by itself not ideal, because now the IC packages are on the opposite side. They're not cool enough. If we look at the RAM chips, it looks like they're okay with any of the different options. Okay, it kind of looks like B and C by themselves can sometimes be better. Let's see, that's blue. Can sometimes be better than all three fans. A little bit lower. It's close on the RAM packages, but it almost looks like B and C is better. So you might look at it and say, man, if I can get away with just two fans and just kind of place them up in the middle and on the one side so it blows directly on the processor, I can save energy consumption and still get the cooling that I need. So might even save us some room inside the part to make this a little smaller. That's really what this webinar is all about, is putting more into smaller places. Just like the Nest, consumers are demanding more features, Wi-Fi connectivity, and they want these devices to be as small as possible. So you can take a look at these numbers again. They're pretty much the same thing. So we're seeing, ideally, actually the B and C. So we're able to change the design, finalize it, check the flow, make sure we're within our chip temperature requirements, and optimize the fan configuration. I'll just click through some of these. These are some of the things that Flow helps us really get done quickly. Sorry. There we go. So it's easy to use, cuts the time out from really manufacturing and making the product before you can figure out what the airflow is doing. Helps you reduce the number of prototypes, things like that. GoEnginneer offers expert training and mentoring programs. We're able to, with our mentoring, we can come on site and actually sit down and help you with your scenarios that you're using Flow for. So instead of going to a training class and learning how to use Flow on something that you'll never run Flow on again, we can actually help you with one of your projects, real-world projects, and figure out what's the best. Okay, so this is what some of our customers in the electronics industry have found. I don't know why it gets light there, but anyway, you can look at basically the things that we've been talking about, improving effectiveness and efficiency of your design, as well as minimizing cost and improving cycle time, because you're able to do more in less time. So they cut 2 to 3 weeks from their tooling development package time. Some of our customers have given us some information about how they've reduced their design cycle. This IDEX Health and Science LLC has dropped their design cycle 50%, eliminated 90% of their prototyping requirements, cut cooling time down by about 6 to 8 weeks. All kinds of different customers. You can talk to your account manager if you'd like to see more companies in maybe your industry that would be willing to talk to you about what they've been able to see in their flow analysis and how much it's improved their design process. I'll just click through some of these. You're welcome to read through them if you'd like. All right. This has been a GoEnginneer webinar. Again, my name is Matt Morgan, Application Engineer at GoEnginneer. Thank you for joining our webinar on electronics and using flow simulation to help improve our electronics design. And in today's technology, where we're adding more and more electronics to smaller spaces. Thanks again, and thanks for watching.